Hello everyone, this is Amit Brambert, your professor for CS110 at Laurel Ridge Community College. Today we are going to go over chapter 14. It's about simulation, graphics, and other applications. Welcome to chapter 14. Here we explore simulations, computer graphics, and modeling complex objects and applications like computer gaming. Simulations helps us study systems that would otherwise be too dangerous, expensive, or complex to experiment with directly. Graphics allow us to visualize both real and imagined worlds. Together, these topics show how computing bridges science, engineering, and entertainment. Throughout, the chapter will look at real world models from weather systems to digital landscapes and examine how simulations drive everything from scientific predictions to immersive video games. We aim to understand what simulation is, why we use it, and what kinds of systems are best suited for it. Many real world systems like ecosystems, traffic flow, or weather are too complex to fully understand through direct experimentation. We will also distinguish between continuous simulations, which model change over time using equations, and discrete event simulations, which focus on sequences of events. Recognizing the differences will help you understand how scientists choose the right modeling approach. We explore how object-oriented design principles help build simulations by allowing real-world objects to be represented as software objects with attributes and behaviors. We'll discuss queuing systems, which you encounter daily, like checkouts, call centers, or car lines. Finally, we'll examine the complexity of weather and seismic models. These systems involve vast variables, chaotic behavior, and extremely detailed mathematics, demonstrating why simulations are essential in scientific research. A final set of goals focus on computer graphics, animation, and gaming. Graphics generation involves understanding light, geometry, and rendering techniques. Animation adds time, requiring smooth transitions and physical realism. Gaming combines all these elements: graphics, physics, AI, sound, and user interaction. By the end of this chapter, you'll appreciate what makes modern visual computing so challenging and powerful. A simulation is a model of complex system that we can manipulate to predict behavior. The real world is filled with dynamic, interactive systems, from weather patterns to traffic flow. Simulations allow scientists and engineers to test scenarios safely and efficiently. A model simplifies reality by capturing essential parts of the system and rules that govern interactions. The strength of simulation is what we can run it repeatedly under different conditions to observe outcomes. Constructing models. Continuous stimulation treat time as flowing, uninterrupted variable. Changes in the system are described using differential equations. Meteorological models are a classic example. They track temperature, pressure, humidity, and wind continuously across time and space. These systems require strong mathematical foundations and high computational power because tiny differences in starting values can dramatically affect outcomes. Constructing models, discrete event simulation. Discrete event simulations break systems into entities, attributes, and events. Entities represent objects like customers or cars. Attributes describe characteristics such as arrival time or size. Events are interactions such as customer entering a line or a machine finishing a task. This method works well for systems where events happen at specific point in time, like manufacturing, logistics, and computer networks. Queuing systems. A queuing system is a typical type of discrete event simulation. It models situations where objects wait for service, like customers in line. These models use random numbers to represent unpredictable arrivals and service durations. A system includes servers and queues. By simulating many cycles, we can predict wait times or optimize staffing. This is essential for businesses, hospitals, airports, and more. The slide asks you to think of everyday queuing systems. Examples include grocery store lines, drive-thrus, elevators, phones waiting on hold, or even internet data packets waiting for processing. Recognizing these systems help illustrate how often simulation supports real-world efficiency. To build a queuing model, we need to know the types of events, number of servers, arrival time distribution, and expected service time. This determines how entities move through the system. Once these elements are defined, we can simulate the flow and measure matrices like wait time, system congestion, or service efficiency. This helps decision makers improve operations. The slide asks you to apply the concepts to a service station. Events might include arrivals and departures, servers might be fuel pumps or service personnel. Arrival times can be estimated from traffic patterns or historical data. Service times comes from measurements. These inputs allow you to construct a model that predicts business and resource needs. Meteorological models rely on physics, fluid mechanics, and thermodynamics to simulate atmospheric behavior. These models start with observed variables such as temperature and wind speed and apply equations to predict future states. Because the atmosphere is chaotic, small measurement errors can grow quickly, limiting forecast accuracy. Still, simulations remain essential for weather